All right, so welcome to the second half of chapter 4. We talked about the Hamiltonian method. We talked about the Jeffersonian method. And now we're going to talk about a few more here. In this section, we're actually going to talk about two, the John Quincy Adams method and the Webster's method. So we're going to cover two in this section. So let's go for it. There's going to be subtle changes between what we've learned so far, but this will be the second half of the textbook here. Let's go with it here. So this was proposed by John Quincy Adams in 1832. Again, a counterpoint to Jefferson's method. And in essence, really, it's the fact that instead of rounding down, which is the Jeffersonian method, the Adams method is you round up. You just make modified quotas smaller then in order to get the divisor that you want to work. So very similar. It's like the flip of the Jefferson method. So let's go with it here. So our starting point is to find a suitable divisor. And what we've done is the Parador's Congress. We've kind of did this one several times already. So we start off with the standard divisor being 50,000. And so what we're going to do is we're going to make this guy 50,500. And so what happens is when you make it 55,500 right here, and what we're doing is we're just always rounding up, up to the next one. So you use your upper limit. And that seems to be, nope, still at 251. So we're going to increase it to 50,700. When you do that, the upper limit gives you all these different pieces here. So how does that help is it allows, really in a sense, more representation from the states. All right. So just because this one right here, 50,700 worked, all of them work from 50,628 all the way to 50,999. All those divisors would work just fine to give you the exact same count. All right, Daniel Webster. I believe he was in education. He also has, I think that's the person that made the Webster's Dictionary. That's Daniel Webster. He proposed, same year as the Adams method in 1832, instead of rounding up all the quotas, Jefferson's, so down all the quotas, Jefferson's method, rounding up all the quotas, Adams method. He just proposed, why don't we just round like we normally round numbers? Why do we have to round up or down? And so same exact process. That's why they're in the same exact seed. We found out that the is the same exact section here. We found out that the standard divisor 50,500 gives you 251 seats. So if you do the conventional rounding of things, you just need to go up another 100. So 50,100 would give you all that you need. So notice this is just the way we normally round. If it's 0.5 or higher, we go up. And if it's 0.5, lower than 0.5, we go down. Or we stay the same. So that one should go up, that one should go up. That's the normal process. And then what we do is we modify it by an extra 100. All right, there it is. Gives us 250. So some homework questions very similar to it. Make the apportionment under Adams' method of the Margarita Congress. And again, notice that in the homework here, you are redoing a lot of things from previous things here. A lot of exercises from previous data you have already done before. And so remember the Margarita Congress is a percentage formula, right? So in this case here, if you used a 0.8138 all the way up to 0.8149, those would have been just fine. And according to the Adams method, you're always rounding up, rounding up, rounding up, rounding up, and you have what you need right over here. Find the appropriate apportionment under Webster's method of Tasmania State University. There it is. So again, you would round this like you normally would round, and then you would adjust. And so it looks like we probably we were over by one. We were over by one. And so any divisor 41.79 is 50.14. Any one of those could be used in order to find the apportionment there. 4.5, the Huntington-Hill method. Okay, here it is where we can get into a little bit more, just slightly more complicated mathematics, not by much though. And so what we do have to know historically is in 1940, Congress did finally set up a exact case scenario. Because what happened was every 10 years, typically political reasons with little consideration of the mathematical subtleties, and one time or another, the Hamilton method, Jefferson method, and the Webster method were used sometime in our history for Congress. So after the census data is passed, they look at all the populations of all the states, and then they decide accordingly. So, but in 1941, the Apportionment Act was passed, and it gave two different provisions, or two main provisions here, that the seats in the House of Representatives will always be 435. And two, the method of apportionment is permanently set to equal the equal proportions method, or what we're going to study right now, which is the Huntington-Hill method. That is it. From here on out, Congress uses this method here. So what is this method? Let's go with it. All right, proposed by Mr. Hill, a statistician, later revised by Huntington, but then it's called the Huntington-Hill method. So Huntington got his name first on the roll there. All right, so what is this? It's a sophisticated variation of the Webster's method. It's very similar to it, has one extra little calculations that the Webster method doesn't. And so they're not identical, but in many, many, many cases, they're going to give you the exact same results. So under the Hilton method here, the cutoff point. So Webster said just make it 0.5, right? So for this one, it is a geometric mean. Here it is. You take the A and the B, you multiply them together, and then you take the square root, and that's going to give you the determining factor of when you are to round up or leave it the same as rounding down. Oh, so what do you do? So given a quota Q, the cutoff for rounding would be given like this. C equals L is the lower limit, Y is the upper limit, and we take the square root after we multiply them together. All right, let's jam. Let's see how this works here. So in each case, around the quota, Q up or down based upon the Huntington rule. So if you have a quota between 9 and 10, notice what happens here. It's a you're going to multiply the lower half and the upper half. The lower quota, the upper quota, you multiply, that'll be 90. Square root of 90 is 9.487. So that would be, instead of 9.5 being the cutoff is 9.487. All right, a few things we've got to consider. The decimal part of the cutoff is always smaller than 0.5, but not by much as you get to some bigger numbers here. The bigger the number, the closer it gets to 0.5. So that's why it's very close to the Webster method. All right. And so practice this with the 50.100 at home when you do that. And then what you're going to do is you're going to multiply to get the cutoff point. So in this case, between 32 and 33, cutoff point is 0.496. So this one still gets rounded up. This was kind of close here. Look at that. This one still gets rounded up. This does not. This does. This does. And this does. Okay. And then notice, wow, perfect. 240. Sorry, 250. So round each of these numbers using the Hamiltonian method. Go for it. So in this case, here it is, 8.589. If you look at this, the 8 and the 9 are between two integers, 8 and 9. We compute that together. We take the square root of it. So square root of 79 is 8.482481374. All right, it's because you take the 8, which is the lower piece, you take 9, which is the higher piece, multiply them together, and take a square root. All right, how about this one here? Between 8 and 9 and 8.485. So we need only to compute 8.485 as a geometric mean. Hey, we get the same number, right? Because it's 8 and 9. And so that which we know to be an 8.4852, notice this is a 0.485, this is 4852. So this number actually is technically bigger. In that case, this gets rounded down to 8. All right, as is in B, 8.484 instead of 8.4852, so it gets rounded down to 8. 8.486, so let's go over here, 0.485, that's lower, so therefore Luba gets that. All right, small country consists of 5 states, A, B, C, D. The standard quarter of each state is given. Find the number of seats being apportioned. All right, let's go with it here. So in that case, between a 25 and a 26, the cutoff would be a 24.4951. This is a 0.49, so it stays. That one stays. This one stays as well. 0.48.482. Nope, that one stays at all. And this one gets to go up. And this one gets to go up. So there it is, putting it all on the block. That's what we have. And 50. The country consists of 6 states. There it is, 1, 2, 3, 4, 5, 6. Populations are given. And there are 200 seats. This is where we're going to do the whole entire piece right here. So find the apportionment under Webster, then find the apportionment under Huntington Hill. Compare them. So take the time right now if you need to. Pause the video if you have to. Try it yourself first, then come back to the video. All right. Let's go with it here. So there is a modified divisor. So let's go back over here. So if we were to get a divisor here, right? It's all this divided by 200,000, or so 200. And you get that. All right. And then according to, this is Webster here. That's going to go up. That was going to stay, go up, stay, stay, go up. All right, there it is. Under the Hamilton-Hill method, we're using that. Notice the cutoff is slightly different. Let me go back real quick here. All right, there's your 0.5, 0.49, 0.4964, right? 0.4939. So that one gets to go up. That one gets to go up. That one gets to go up. That one, no. Yeah, I'm sorry. Yeah, no, that's a 1 and that's 6. Yeah, gets to go up. And that one gets to go up. So let's see the difference there. Yeah, this one gained an extra seat. And that one gained an extra seat at the expense of the small ones here. Okay, just want to go through that with you as well. And then modify the divisor by choosing that one. You actually have to just go one out. That's it. So if you chose 10,001 as your cutoff divisor, everything works out just perfect. All right, and the last section for us. All right, quotient rule and the appropriate paradoxes here. So just like the last chapter we covered, what does it mean to divide out something evenly. We find out there is no fair value. It's, oh, sorry, the vote. That's right, the vote. How do we vote? And so there's really no fair vote. What do we do is we just get up all the ways you can vote and how you count and how you separate what can be counted. Okay, so 4.6. Let's go with it here. A little bit of definition here as we go through it. So first things first, here's the key facts about the appropriation method as discussed in this chapter. So I'll let you read it for yourself. All right, so the Hamiltonian method does not violate the quotient method. Hamiltonian's method can produce appropriate apportionment paradoxes, though, given results that are unexpected or seem to violate common sense. It is important for an apportionment need to both satisfy the quotient rule and not produce an apportionment paradox. Okay, let's jam. So just kind of the different kind of rules that are set in. So the quota rule just says this: every state should be apportioned to either its low quota or its high quota. There it is. So for an example, if a standard quota is 38.72, it could either stay as through 138, you can go up to 139, but that is it. It should not go beyond those. That's the quotient rule. There's also the upper quotient violations. So if you go beyond the 139, you hit a 140, you have succumbed to the upper quotient violations quota. The lower quota seems to kind of say the same thing. If you're 138.72, lowest you can go should be 138. You should never have a calculation that gives you 137. So the Hamiltonian method satisfies the quotient rule. Starts by rounding all the standard deviations down, which is lower, and then awards the extra seats according to the up. The Jeffersonian does violate it. The Adams method violates it, and the Webster-Huntington method violate the quotient rule. Very, very rarely, just the way it's made. All right, and then apportionment paradoxes. Again, things that seem to be non-logical in our thinking here. So we have the Alabama paradox. Most likely something happened in the state of Alabama. But this occurs when the state gets apportioned fewer seats simply by virtue of the fact that the total number of seats being apportioned has increased. So the number of seats increased, but then theirs now went down. It has to do with the divisor. The population paradox says this: when paradox occurs when the state gets apportioned fewer seats simply because of the fact that their population has increased, so that you have more people in the state. And then when you take a test for them, when the population has increased. All right. And just taking a look at this little piece, let you guys read it here. All right. So the apportionment of 25-25. We go there, shown in billions. There it is. Under Hamiltonian's method, everybody gets the lower quartile. Then the ones with the highest one, 0.6, 0.388, they get the extra seats done. Part 2, 10 years later, there's another thing that happens here. Census is made, and it says that we have some changes in our population. So what happened was an increase of 8 billion in Coney and a 1 billion increase in population of Elysium. And what happened was populations of the plants remain unchanged. But because of technically the divider, the way things are divided, it does show some problems. So notice that the total population increased to 909 billion. So now our divisor slightly changed to 18.18. If we do that, what happens is things change because you're no longer in that little bout anymore here. So 909 is raw data. This is just the addition of all this. So this divided by this gives you that. So this divided by this gives you that, yeah. All right, so if you take the lower quota, and then you add 2 more over here as a surplus, it gets you where you need to be. All right, one remarkable thing about the 2035 apprentices is that Elysium actually went down in seats. Their population went up. Beta gained seat even though its population remained unchanged. Does that happen? It's because the divider changed, right? All right, and then some interesting things here. Elysium then used this apportionment as an excuse to invade beta. And the years of peace were over. Sad, sad. All right, the new states paradox. Again, paradox comes in when the state's apportionment is affected simply by virtue of the fact that a new state, together with its fair share of seats, has been added to the apportionment calculation and then throws everything off. So the Metro Garbage Company has a contract to provide garbage collection recyclables to 2 different districts. There it is. They run 100 trucks. And if you do that, you are divided out this way here. So North Township, because of 10,000 homes roughly, they get 10 garbage trucks. Southtown, because of their 89, over 89,000, they get an extra little piece there, and everything's at 100. So would you say that's fair right there? Now imagine the Metro Garbage Company is bidding to expand its territory. And here's the population paradox. So by doing that, what happened was this went to 11. And this is a 5. So this one got an extra seat. This one had already the 89, but this one has the extra seat. All right, and then just a summary of all this, where and which one is violates. The various rules there. All right, of the 5 methods, Webster's method and then the Hamiltonian method are used in some sense the best because, well, in theory, they violate the quota rule, but they hardly ever do it. And then there's a connection between the rules here, which I think there's some questions on it here on the homework. So that are there any apportionment method satisfies the quotient rule can produce paradoxes, and any apportionment method that does not produce paradoxes violates the quotient rule. I'll let you think on that for a little while. So let's take a look at some homework questions. So if the standard quota of state Y is 7824, then which of the following apportionments for state Y it is or are possible under Adams' method? Go for it. Try it yourself first. And we're back. So let's go with it here. So the correct answer is A. Choices B and C represent upper quota violations. Adams' method can produce only lower quota violations. And since 78 or 79 could be possibly apportionments, choices D and E are also eliminated. So again, it's kind of where's the correct choice from this? So working backwards from where you were. Okay. I have I think we're doing 60, but we have to reference back to 20. So this is 20 from earlier. The exercise refers to apportionment of nurses to wings and Plainsville Hospital, introduced in exercise 20. Here's exercise 20. The answers to part A and B in exercise 20 are illustrations of which paradox? We need to look at the parts. And of course, if you do not have exercise 20, here it is right over here. So there it is. Number of beds is 145 for A, 66 for B, and 30 for C. Standard divisor, add them up, divide by 20. That gives us your standard divisor. And from there, you look at these people here giving you the lower quartile. Sum is 19. So you have 20 minus 19 is 1. Nurse remains to be allocated. This is given to C because it has the largest fractional part. There it is. The final Hamiltonian representation is done. 12, 5, and 3. Back over here. Suppose is additional nurses hired to the hospital, bringing the total number of nurses to 21. Use Hamilton's method to do the appropriation for the nurses. And then compare your answer. All right, with B, let me just kind of back up just a little bit here. Be suppose additional nurses hired at the hospital, bring the total number of nurses to 21 instead of 20. Use a Hamiltonian method. Again, there it is. You divide by 21. This is 11.9. If you do that, there it is. The lower quota are 12, 5, and 2. Sum is 19. So we have 2 nurses remaining to be allocated. These are given to wings A and B since they have the largest fractional part of the quota. Again, Hamiltonian appropriation. Apportionment. When the staff consisted of 20 nurses, wing C was assigned 3 of them. So an additional nurse was hired, so wing C ended up with the 1 fewer nurse. Again, that is an example of the Alabama paradox. And if you want to, you can kind of research a little bit more on the Alabama paradox. What was that? All right, with that, we are done with chapter 4. Oh, sorry, here it is. Oh, no, one more. Oh, that's it. That's the answer to 60. The Alabama paradox. Number of nurses assigned to wing C went from 3 to 2 with no reason other than the fact that the hospital hired an additional nurse. There it is. All right, and hopefully you guys are all at the end of chapter 4 as well.